Okay, so these types of problems involve two steps. In the first step, you're going to draw your chair with the substituents pointing either up or down. You don't care about axial or equatorial at this first point, okay? But in the second step, you are checking for stability, so this is where you do care about axial and equatorial. If it's not the most stable conformation, then you're going to do a chair flip to change all the axial substituents to equatorial and all the equatorial substituents to axial, okay? And that finishes up all the types of conformational isomers you'll ever see. For straight chain compounds, we saw anti-staggered, gauche staggered, and eclipsed conformations. For rings, we saw that a ring can be either planar versus puckered, or it can have its substituents be axial or equatorial, okay? So this brings us to the third and last type of isomer. And this type of isomer, for sure, you're only going to see in OChem. And these are called stereoisomers. So let's erase some of this stuff and we'll get into that. Okay, so we've been talking about the three different types of isomers you can have. The first type was constitutional isomers, and these differed in connectivity. The second type was conformational isomers, and these differed in their bond conformations, how their bonds were oriented. Our third and last type of isomer is known as a stereoisomer, and these are going to differ in the spatial arrangement of their atoms. So let's go ahead and write that down. Okay, so stereoisomers, these are going to differ in the spatial arrangement of their atoms. They're going to differ in their spatial arrangement. Okay, so stereoisomers differ in how their atoms are arranged in space. And let me just tell you that not all compounds are going to have stereoisomers. Almost all compounds can have constitutional isomers and conformational isomers, but it takes a special compound to have a stereoisomer. That's what's so cool about these guys. In order for a compound to have a stereoisomer, that compound has to be chiral. It has to express chirality. And what does this mean? What does it mean to be chiral? Well, let's write this down. Okay, so a compound has to be chiral in order for it to have a stereoisomer. And what is a chiral compound? A chiral compound is any compound that has a carbon bonded to 4 different substituents. Okay, so hey, let's write that down. A chiral compound, this is any compound that has a carbon bonded to, and this is the key part, 4 different substituents. Okay, so let me show you an example of a chiral compound. Okay, so in this compound, we've got a carbon bonded to a CH3, a Cl, an OH coming out at you, and a hydrogen going away from you. Okay, and if you look at this thing, you'll notice that this carbon in the center is surrounded by 4 different substituents. An OH, a Cl, a CH3, and an H. Each one of these substituents is different, and so we would consider this compound to be chiral. And hey, just to give you some vocabulary you might hear, this carbon in the center that's surrounded by these 4 different substituents, this is known as a chiral center, or another name for this is a stereocenter. Okay, so if you want to write that down, this carbon that's in the center, surrounded by these 4 different substituents, this is known as a chiral center. Chiral center. Or you'll also hear this thing be called a stereocenter. Okay, and just for the sake of comparison, let's go ahead and draw up a non-chiral compound, also known as an achiral compound, a compound that doesn't have a carbon surrounded by 4 different substituents. And this would look something like this. Okay, so this compound's got a carbon in the center, bonded to a CH3, bonded to a chlorine, another chlorine, and a hydrogen. And if you look at this compound, you'll notice that this carbon in the center is surrounded by 4 substituents, but 2 of them are the same, this chlorine and this chlorine. And so we'd say that this compound is achiral. It doesn't have a chiral center. It doesn't have a carbon surrounded by 4 different substituents. And hey, you guys, if this guy isn't chiral, then can this compound have a stereoisomer? No, right? You can't have a stereoisomer unless you're a chiral compound, right? Okay, so hey, that was just for the sake of comparison. Let's talk more about chiral compounds now, because those are the ones that do have stereoisomers. So let me go ahead and erase this guy. Okay, so do me a favor and draw an arrow coming down from this chiral bullet, like this, and go ahead and write next to here that if a compound is chiral, ... it has an enantiomer. It will have an enantiomer. And what is an enantiomer? Well, an enantiomer is just a non-superimposable mirror image. Let's write that down. An enantiomer, this is just a non-superimposable mirror image. And to explain what this non-superimposable mirror image thing means, let me draw out the non-superimposable mirror image for this compound that we saw earlier. Okay, so let me go ahead and erase this right here, and I'll draw this non-superimposable mirror image up side by side so we can compare these two. Okay, so we said that this compound has a carbon with 4 different substituents. We said that this guy is chiral. And hey, if compound is chiral, it has an enantiomer, a non-superimposable mirror image. And this is what I've drawn up for you here. So hey, this dotted line right here just represents a plane. And if you look at these 2 compounds side by side, you will realize that they are mirror images of each other. You may not see how they are non-superimposable just yet, but you should at least be able to see that these guys are exact reflections of one another. On this compound, you have a chlorine on the right. On this compound, you've got a chlorine on the left. On this compound, you've got an OH coming out at you to the left, and on this compound, you've got an OH coming out on you to the right. And the same thing goes for these 2 hydrogens, okay? The point is, you guys, is that these 2 compounds are exact opposites. They are mirror reflections of each other. But hey, that's not what makes them special, because hey, everything has a reflection, right? You guys, everything has a mirror image. So what makes these 2 compounds special, why we give them the special title of enantiomers, is because these compounds are non-superimposable. And let's see what this means. And a really classic example of something that's a mirror image but isn't superimposable is your hands. So hey, take your right hand, hold it up, take your left hand, hold it up, and look at your 2 hands. Your 2 hands, unless you have like a 6th finger on one of them or something, should look like mirror images of each other. But hey, even though your hands are exact reflections of one another, you'll also notice that no matter how hard you try, you can't superimpose one hand on top of another. What this means is you can't put one hand on top of another and have all your fingers oriented in the same way. Like your thumbs, they're not going to be directly on top of each other. Your pinkies aren't going to be directly on top of each other either. They aren't superimposed. And this is the same thing with these 2 compounds. These 2 compounds are exact reflections of each other, but no matter how hard you try, you're not going to be able to put one compound on top of the other and have all the atoms oriented in the same way. You might be able to superimpose a couple atoms on top of each other, but you won't be able to completely superimpose all atoms of the compound.